Hello again, folks, in 114. Today we're going to be starting a new chapter. We'll be covering sections 7.1, 7.2, and 7.3. Okay. Here's again, as always, the calendar. Today is March 3rd, so we're right on schedule. Very good. We have one more week and then there's spring break. If you are inclined to follow along in your notes, maybe fold over paper like this with the corners towards the center here to make a little border. All right, this will basically be the point of material building, starting, the point starting and building towards test number 2. Okay, so test number 2, I want to say, is chapter 7 and chapter 8. All right. Incidentally, there's a new batch of my lab assignments. So if you log into Canvas, our Canvas course, you'll notice that there's a date. It seemed to me appropriate to give you, just about a month again. Right? It's a little bit less material than last time, but here's how I figured it. If today is the 3rd, right, I gave you until March, pardon me, this would be April technically. Here's March 31st, April 1st, April 2nd. The evening of April 2nd going into Saturday, April 3rd. So figure midnight on technically April 3rd. All right. The very, very morning. Right. Anyhow, the packet that you want to print looks like this. We're talking about the metric system, so I made this table that I want to give to you, and I'm going to fill it in with you right now. When you're actually doing your work of converting between metric units, you might just use these sort of horizontal graphs. All right, but this I want to give you and show you just to establish the prefixes and the roots, the units basically. This is not something that will be immediately important, but it will be basically a reference of a lot of conversion factors. There are some conversion factors in these 3 sections, but you're not really to worry about that until section 7.4, which is next week. All right. Anyhow, this is an overview. Naturally, I stole this from a notebook. All right. The inside cover of a marble notebook usually has information like this, and I thought this was quite comprehensive, so I swiped it. There's a typo here. I believe there's supposed to be an R after that I. Right? So whoever made this, they did a nice job of doing this, but they didn't edit. Maybe I'm wrong. Maybe there's 2 different ways to spell that. Avoidus, I think it's pronounced. So there's actually an R in it. Anyhow, at least according to dictionary.com. All right. There are some diagrams here. What I thought was pertinent from section 7.1 and 7.2 and 3. And this is something that I think I had alluded to at least once before. All right. Again, when we get to section 7.4, I'm going to use this model a lot. All right. But I might do it a little bit later today, so I figured let me at least show you that. Here's a formulas page, all right, for converting from Fahrenheit to Celsius and Celsius to Fahrenheit. And just to give you, fellow Americans, a feel for the Celsius scale, because pity us, rest of the world, we don't use it in ordinary life. You have to sort of, wean yourself, at least insofar as the math is concerned. Wean yourself off of the feelings that you have about a certain number. So like if you told an American, oh, it's 20 degrees out, they go brr, right? Because they grew up with that number, all right, as being cold on the Fahrenheit scale, all right? Whereas 20 degrees on the Celsius scale, as everyone else probably knows, is room temperature. So not brr, no brr, all right? Anyhow, here are some examples for converting those temperatures, all right? All right, so let's get started. Following along, do print that out. We'll get busy. All right. Where are my glasses? Okay, over here, where they shouldn't be. Take a sip of water. Alright. Well, that is much more cooperative today. May have to get out the new colors. The old ones are getting crummy. Let me start with this. There are systems of measurement, and I want to give you sort of an overview, as I like to do. Let me do this ahead of time. Eventually, I'd like to get around to drawing this in PowerPoint as I do my other charts, but this only occurred to me more recently, so I haven't gotten a chance to do that. So I'll do it by hand. All right. There are systems of measurement. And since I'm teaching this for American students per se, that exists in the United States. I hope you will excuse me for confining myself intellectually for a moment. Right. We are, believe it or not, here aware of other systems, but the system that we use currently and we have traditionally comes from the British Empire, which is why it is aptly named the Imperial System. That is the system of feet and yards and so forth and miles. The Imperial System. I think perhaps because of the Revolutionary War and bad blood between our two nations at one point, we have sometimes referred to this alternatively as the customary system. It's what we do, you know. But we were a former colony of the British Empire, so it really is the imperial system to anyone else outside the United States that is also familiar with it. All right. The system that we are going to discuss by and large today is the System, if I'm pronouncing correctly, accent mark, International and this is where my French gets pretty bad. I'll spell it. Unites with the accent mark this way. Des units. It's not units. That's not how you pronounce that. Des units. I forget exactly. Do forgive me, French-speaking people, even though I myself have some French-Canadian ancestry. English is sadly the only language I know. Anyhow, no disrespect, but the alternative that we often refer to this as is the SI, or metric system. Hence the name of the chapter. System International des Units, I believe is how you pronounce it. SI metric system. All right. Standard International is literally the Standard International System of Units. All right. Or otherwise known as the metric system. All right. Now, interestingly, parts of the imperial system, just to kind of again place us in time, let me put this light on. Get the glare off us here. Give this inner light here. turn this lamp. Let's close the door. The parts of the Imperial System actually come from, the ancient. As a person who is interested in history, that's fascinating, I think. Okay. Even like something like, specifically the Romans, I would say, because of the profound influence of the Roman Empire. All right. Miles, say for example. All right. We still use miles. All right. Now we probably have a slightly different, more precise definition than the Romans did. A mile to the Romans was roughly 1,000 paces, but what do you mean a pace? Is that a pace? It may vary from a person to a person. All right. Whereas now miles is specifically 1,760 yards, or 5,280 feet. Right. So there's a little greater degree of exactitude, but the concept of a mile is dating back from way long ago. All right. That doesn't make it bad. All right. It just means that it's been a tradition we have kept for a very long time. Kudos to us. Now, as for the international system, all right, the SI units, the metric system, all right, this comes from the French Revolution. That's its origin. So 1790, just about, circa. Much more recently in time, all right? And because of that, all right, the French Revolution follows the Enlightenment period. So at least in Europe, all right, where the revolution occurred, all right, there were plenty of people who were interested in the fields of science, right? So when the opportunity arose to refine our system of measurement, which is the foundation of all science, they took it, they took the chance, and they gave us a system that is arguably better, all right? I would, as a person who was a science major myself, I have to agree, this is the better system of the two, all right? Now, why? All right? All right. Well, this is the better system because it's based on 10. It's based upon powers of 10. All right, and 10 should be very intuitive to us, right? Humans, right? Counting by 10s is certainly easier. Because it's based upon something that is familiar and easily predictable, all right? All right. If something is based upon 10, what does that really entail? I mean, it's just moving a decimal point. There's really less memorization involved in it. All right? If you want to convert from one metric unit to another, right, you're just moving a decimal point because you're either multiplying by some power of 10 or you're dividing by some power of 10. All right. Anyhow, eventually I have hope that the United States will conform to this system, even though we've been one of the last of maybe 2 or 3 holdouts for 200 something years. Very stubborn here. I don't like to throw away traditions, right? They have their place, I'm sure, like cooking, for example. In the field of cooking, right? When you have a recipe, it's something like, well, you need 3 tablespoons of, such and such fluids, or, cups. That's not scientific, all right? But, and what the system we have for, cups and pints and such for cooking works, right? A system, as long as it is established and is consistent, right, is functional. There's really nothing wrong with it. But when you're dealing with science and engineering, something that is global, I mean, we really must conform ourselves to this. It is the better of the 2 systems. The problem with this, the imperial system, in spite of its familiarity, is that it requires a lot of memorization. There are vast facts, you know, that you would have to assimilate, right? Right. Specifically, conversion factors. Right? And that becomes arduous after a while. That is the reason why, even preemptively, I included this in the packet. Right? Over here on the side is a brief description of the metric system, really. Right? That's encapsulated here. But virtually everything else, short of the multiplication table, all of that, all right, is the conversion factors for the imperial system or something related to it or concurrent. All right. So depending upon what task you have, cooking, you know, carpentry or what have you, all right, you may be quite burdened. All right, going, this is what this is, and this is what this is, and this is what this is. All right. When we were kids, me, I should say, this is what we were taught. You know. 2 cups equals a pint, you know, 2 pints equals a quart, 4 quarts equals a gallon, things like that. All right, but beyond gallons, I couldn't tell you how many gallons are a barrel. I'd have to look it up, right? I know 1,760 yards is 1 mile, and 5,280 feet is also a mile, right? But if instead we use some alternative system based upon powers of 10, I really wouldn't need to know that. It wouldn't be as arduous. There'd be less memorizing. Anyhow, we have our traditions. Yes, we were a colony at one point. No disrespect to them. All right, but the French system, the Standard International System, SI metric system, is the better system. All right, to be sure. All right. It's an interesting thought I had. What's an example of what, now, I've described this as systems of measurement in the U.S., right? The metric system is in the U.S. It's just not an official system, right? When you see street signs around here, they're in miles, you know, the speed limit is miles per hour. Distances between 2 points are in mile markers, like the Romans, all right? But in the 70s, all right, there was the idea that eventually the United States would convert entirely to the system, and we haven't, all right? Where does it exist? You may laugh at this, but where does the metric system exist in the United States? In Coca-Cola and in Pepsi, right? And in other sodas. When you go to the grocery store here, the supermarket, right, and you buy soda, I would advise you to steer a little away from it. It's a lot of sugar. All right, it's in liters, right? Now you could get something in fluid ounces, of course, still. Right? In fact, it might even be on the same bottle, but the bottles, the largest bottles, are in liters. All right, that's the metric system. Right? Now, why do you suppose that is? All right, I don't guess that. Coca-Cola, being the company that it is, right, standardized itself at one point strategically to say, okay, well, we sell Coca-Cola in India, all right? We sell Coca-Cola in Mexico. We sell Coca-Cola all over the world, all right? It may have originated here, all right? But it's a global brand. So it is to their benefit not to have 2 different systems, all right, when they're manufacturing. Plus, they manufacture in different locations as well, you know? They produce Coca-Cola overseas. They don't just ship it from here. Anyhow, beware of that. All right.
Doctor, do you remember what day it was sent out?
All right, let me give you another diagram to summarize. There are, and again, I'm going to sort of give myself little boundaries here, so humor me for one moment. I'm going to divvy this up. You know, if I had any sense, what I would probably have done is increment the top of my board here so that I can get exactly halfway and into thirds and have you, but that is an afterthought I will have to consider. Hindsight is 20/20, they say. So, if you are following along, and I would never force this, maybe fold your paper into quarters, just to organize the information you're about to get. Alright, now what I want to talk about are that metric units exist for different physical measurements. Right? So I'm going to give that as a sort of the heading. Metric units for lowercase different physical measurements. There's a little balloon here. It's a bit close, but I think you get the idea. Okay. Now, there's measuring distances. So I'm going to make this the head of this column here. There's a certain metric unit you would choose, right, for distance specifically. All right. There is an alternative metric unit for capacity. Another unit for mass. You know what? Let me just change the color of that if I may. And temperature. Okay, so depending upon you're looking to measure distances, capacities, masses, or temperature, you would choose a specific unit, just as you would obviously in the imperial, i.e. customary system, right? We use feet to measure lengths of something, which is arguably distances. Not arguably, it is. Just weird, small distances. Mention that point A and point B where you live. I live at point A, 1 foot away from point B. I'm being silly. Anyhow, we have different units in the familiar system, for different purposes, and there are different units for different purposes in the metric system naturally. Now, I want to be a little bit more vague for a moment. Let me get out my nice markers, since these are being kind of crummy. I don't think I need the red yet. The black and the blue. That might be necessary. Okay. A distance is really a length, right? Here's an example of English having many alternatives to describe basically the same concept. In English, we say distance when we're talking about very long lengths between places, all right? But a length is what it is, right? Now, bear in mind, a length is something that you might refer to as one-dimensional, so let's just call it 1D, right? And it's the basis for things that are slightly more complicated. So an area is based upon length, right? I'm going to encapsulate that. It comes from this, right? This is the next logical step. When you're talking about an area, you're talking about something that is two-dimensional, right? And in theory, right, a length could also be given a third dimension. That is a length this way, a length this way, and a length this way out towards you. All right? In which case you may call it a volume. And I'm purposely encroaching upon this other column here because that is exactly what a capacity is. All right? A capacity is a volume. All right? And it's not 2D or 1D, it's 3D. It's a real object when you're talking about volume, generally. Okay? So distance is really length, and length is the basis of two other things. With two lengths that are in different planes, you know, well, they're in the same plane, I'm sorry. Right? The two lengths, right, you form an area, right? If you have a third length, right, you would get a volume ultimately, right? This is just multiplying two things, that's multiplying three things, right? Why belabor the point? Well, since we're discussing different physical measurements, different units are what we have to consider, right? For distances, lengths, right, we use meters, right? And I'm spelling it the American way, right, which is M-E-T-E-R, right? Thank you, Noah Webster, right? It would be R-E, right, probably because of the French origin. Anyhow, that is abbreviated M, right? If an area is two lengths multiplied, then it would be meters squared. Meters times meters, which would be abbreviated M with a little superscript of 2, of course, right? This is a way that you can tell that you have an area without someone ever explicitly saying it to you. If you stare at the unit and you see a little exponent of 2, you go, that's an area. Has to be, at least if it's meters. All right, and as I said, if we're talking about one-dimensional things versus two-dimensional things and now three-dimensional things, if you are using meters to express a volume, then this would be meters cubed, all right, which is M3. The thing is, when it comes to capacity just standalone as a concept, there is the go-to unit, not just this one. I'm going to put a bullet point here. The actual unit of choice for capacity would be the liter, right, as I mentioned in soda. And again, I'm spelling it the American way, so forgive me if it seems silly. All right, I live here, all right? Liter, all right? So this is a capital, at least historically, a capital L, all right? Your textbook, all right, uses a script L, right? I don't know if that's some change that I have been unaware of, but in recent time. But just understand that these are the same unit, liter, okay? If you're just dealing with capacity, you know, assume probably you're going to be using liters. But you, as an alternative, all right, can also express the same volume, all right, using cubic meters instead. So this is a situation where there are two options, okay? Cubic meters, if you're basing it upon lengths, or liters if you're just dealing with a fluid, you know? This is more or less when you're dealing with a solid, and this is more or less when you're dealing with a liquid, right? But one can be converted to the other very easily. Then there's mass, right? Now, this warrants a conversation unto itself, and I'm going to give you another diagram a little bit later. Just for right now, realize, mass is not weight. All right? People conflate the two because they're related, right? Basically, mass and weight are proportional. One cannot exist without the other, right? But they're not exactly the same thing, right? So just to give you a heads up, you're probably aware, if you've ever taken a science class, at least through high school, you most likely know this already. But your mass is going to be the same no matter where you are, right? That's the amount of material matter that you're made of, basically. Your weight, on the other hand, will change depending upon your proximity to something much larger than yourself, like the Earth or the Moon or what have you, right? The Moon, for example, has 1/6 the gravity of the Earth, so they're not weightless when they visit the astronauts, but they weigh less even while their mass is the same in both places. Okay.
0.4.
And then there's temperature. All right. Well, the unit for this is the gram. When you think mass, think grams. All right, which is abbreviated as lowercase g usually. All right. So you have meter as the base unit, liter as the base unit, gram as the base unit. I assume that's probably why the textbook is using a lowercase l for liter rather than a capital L. All right. The temperature, the Celsius scale is used.
You too, Dr. DeWitt. Have a great day. Bye-bye.
Right. And again, if any American, if you come across them, resist converting to or using the Celsius scale versus what we were taught here, which is the Fahrenheit scale, do forgive them, because this is evidence of math really being a part of your life without you really realizing it, without you truly realizing it. We have grown up with a feeling basically associated with certain numbers, right? As I mentioned before, 20 degrees to an American is intuitively cold, right? But because we're thinking in Fahrenheit, you know? So mention the number to them and to describe the weather and they will go brr, you know? But to everyone else on the planet that's using Celsius scale, 20 degrees is comfortable, all right? So the difficulty in getting Americans, especially older Americans, to convert to some newfangled system, new isn't 200 years, is that you're fighting the feeling that they grew up with, all right? As a teacher, you need to be aware of this, all right? You're gonna have people that come up to you and say, this is stupid, why are you telling me my kids this? Because the rest of the planet does this, all right? And it's important, all right, especially in science and engineering, all right? So anyhow, just realize that you're fighting the feelings, the emotions of people. They're not being rational, all right? So give them a little bit of comfort, ease them into it. Maybe if you start them young enough, they won't notice, all right? Now 20 is room temperature on the Celsius scale. Sorry, not to make a debate about it, but it is important, and in my own career as a teacher, I've had parents come up to me and say to me, "Why are you telling my kids this stupid metric system?" Why is it stupid, you know? Because you're not familiar with it. People are scared of things that are alien to them, right? So you got to give them a little level of comfort somehow, all right? Be careful. Anyhow, Celsius scale is the temperature scale of choice, and it would be the unit of degrees, a little naught symbol, in superscript, and then C naturally for the unit. Okay. Other things that you have to be aware of, and I'm going to put it up here. We have conformed to, we in the United States, I should say, conform to this standard, all right? We use commas. So for example, up on this side, I'll put the US when we're talking about something like a decimal 3.5, all right? And in other places on Earth, perhaps things were not imperially based, all right, would use a comma instead. We use, other parts of the world use a comma, whereas we would use a period, right, as a decimal point, right? So just be aware of that. So, and vice versa, right? Globally. Right. I don't think there's anything wrong with our system in this regard. I do believe in being self-critical. It's very important. But I wouldn't say that this is an instance of where the United States is being backward at all. All right. All right. But But just think of these things as being the same thing depending upon where you're standing, all right? This is the norm in the United States. We use periods for decimal points, whereas some parts of the other world, if not the entirety of it, I haven't been anywhere else except Canada, all right, is comma, all right? So in a sign, for even a very large number, I'll put this in blue, if you saw something like 3 billion 644 million 700,000, right? This would be the way that we write it here. All right, we group things in sets of 3 on the left side of the decimal point. Right? These are where the whole numbers exist. And the things that are to the right of the decimal point are the THSs, the suffixes like tenths, hundredths, thousandths, and so forth. All right. In other parts of the world, what you might see alternatively is this. All right, same number, 3.644.700. All right. All right. What I'm getting at is that, again, and I'm not verbalizing it too clearly, I suppose. All right. The metric system uses a comma in the way that we use a decimal point, right? And vice versa. We use commas to group sets of 3, all right? In other parts of the world, you might see, all right, decimal points separating things in groups of 3, okay? The only deviation from this, and I think it really is your textbook's choice, option that they're exploring, is that they will occasionally, when you have a 4-digit number, write something like this. Like 2700, right? They won't bother to put a comma, all right? I don't like that personally. I think that's being lazy. But the argument is that it's easier to read that way. Take that with a grain of salt, all right? All right, so let me verbalize this, just not to confuse anyone. I'm not really awake yet. I need a little more coffee, I think. All right. Just beware, Americans, right, that globally, all right, the metric system may use a comma in the way we use a period. And vice versa. Okay? This is intuitive to an American student. 3.5 is 3 5/10, right? Or 3 1/2, you might say. Sorry for the reflection. But this means exactly the same thing, just using the alternative symbol, 3,5. Right? Of very large quantities. Geez, I really abbreviated that, didn't I? Yes, 3,644,700. All right. All right. It's funny how I left out a bunch of zeros. I'm sorry. I called this billion before, but it's 3 million because I didn't put 000 here. 3,644,700. All right, is 3,644,700. All right, but instead of using commas, we use the rest of the world may use periods in this regard. Okay, so beware that globally the metric system may use a comma in the way we do a period. All right, and vice versa. Okay, so their comma in theory would be here if there was an extra digit, right? Okay. Wake up, Siglo. All right, and again, just in your textbook, you may see 4 digits, not grouping 3 with a comma. It's an option that this textbook uses. All right. All right. Now, let me turn on my projector and give you some root words and prefixes that you could use. You'll see what I mean. Okay. I have to update this later. Here's another course we could use in thinking about the way that you would refer to a number, like say billion and trillion. Right? In the United States, we have a certain way of saying it, and then historically, at least in England, it's the opposite. You know? Some of that is because the discrepancy is because, again, of the revolution. As a former colony of the British Empire, right, when we became independent, we purposely changed the spelling of things, right, which is why things like checkers, all right, CHECKERS, right, is spelled that way here, right, but using a Q and a U elsewhere, right. And then things like the number a billion and I want to say a trillion are exactly the opposite in terms of the number of zeros. Don't quote me on that, but I believe there is a discrepancy when it comes to numbers of a certain size. Right? Beyond a million, right, is what I'm getting at. We thankfully have a consensus on a million being 6 zeros. Okay, so minimize this. And then watch this. Okay. I need to turn this off. And the light's behind. And the light over here. Alright. This is the sheet I wanted to fill in with you. Alright. What is really most important is the amount of space. I have to shrink this slightly. Basically, from here to here is the scope. That is the regular use of units. Right? I have these extra steps above and below, and I have these extra scales that you see over here. And I would indeed, when you're actually converting, if you're not familiar at all, use these horizontal scales, not the system I have here. I'm going to give you the system I have here only for the reason that I can show you what the names of these are. Right? So what I like to do is start with the base. Right? Again, we have measurements of distance, really, length, right, capacity, mass, and temperature. Right? So what I want you to put in here, in this thing that says base units, are basically those things with a little hyphen. Right? So meter and its unit, abbreviation, liter, and I'm being sort of stubborn here, maybe myself, capital L, because that's what we were taught in chemistry, and gram, right, and if necessary, degrees Celsius if you want it to fit it, right, hyphen, 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 right. These are the roots, basically, right, the root unit, if you will, the base units, right, and depending upon the size of the unit, the size of the measurements, right, you will affix, right, the prefixes that are either above or below these, right. So again, there's a way of using this drawing that I'm going to give you for the sake of conversion, but I think the real practicality of just having this table that we're building is just to familiarize yourself with these names, right, the labels, right. That's the only reason I mentioned it to you, all right. Now down here, all right, and I'll put a little color in this to make it a little bit more obvious, right, are the units that would be smaller than these in terms of their size, right. So you would have firstly, just underneath a meter, you would have deci as the prefix, which is abbreviated D, and then put the hyphen this way. So it would be decimeter. Right? And then underneath that, pretty much, here's again, where the metric system exists in our lives here, perhaps unbeknownst to us, centimeter. I think you would be hard-pressed to find an American that does not know what a centimeter is. Right? Why? Because every ruler that you've ever purchased in your life has inches on one side and centimeters on the other. All right? Why do people go, damn America? You know, like, just get a little patriotic for the wrong reason, you know? Centimeters, right? So centi is the prefix, and that's the root, if you will, right? And then underneath that, again, we're all familiar with this, millimeters. So milli, all right? Which unfortunately uses the same abbreviation, right? That is something that happens a lot, I have to say, in math, right? You will see the letter M in one style or another used quite a lot in mathematics, so that is unfortunate, but this is what we have. If you see two M's in sequence, it is understood as being millimeters, of course. If you see a CM, then it is centimeters, and technically decimeters, which is 10 centimeters. Okay? That's if you're going down. So things are getting smaller this way. Right? Now above, and I'll put this in a different color here, right? Or something similar sounding to a meter, is deca. All right, which is DA, da. All right, hyphen that way. Okay, so you could have a decameter, a decaliter, a decagram. All right, above deca is hecto. H, right, is a prefix. All right, and then what probably is familiar to an American somehow, right? Kilo, right, which is K. Is that, right? Kilometers, kilometers, little accent there. Kiloliters, technically kilograms, right? Kilograms is probably more familiar, all right? All right. Now, in theory, with just this information, all right, you could use this scale, all right, to convert from, again, assuming you're a person that is unfamiliar with it at all right? You can convert from one unit type to another by counting steps, all right? That's what these arrows are here, all right? If, essentially, you are moving from a larger unit that is higher up to a small unit that is down lower, you move the decimal point that many spaces to the right. So hypothetically, if you're going from meters to millimeters, you will start here and count 1, 2, 3, and move the decimal point to the right 3 spaces, all right? Believe it or not, this is how I was taught this back when I was like, 10 or 11, all right? Anyhow, it isn't bad, but again, there's a better system I'm gonna show you momentarily, all right? Now, over here, like let's just say you were going from a larger unit to a smaller unit to a larger unit, right? Again, that's what these arrows here are referring to. If you're going up the scale, you move your decimal point left that many spaces. So let's just say hypothetically, worst case scenario, going from milli to kilo, all right? 1, 2, 3, 4, 5, 6 is the maximum usually, okay? So you would make 6 waves this way, all right? Now, let me just show you the scale here because I genuinely think the horizontal perspective is superior to the vertical perspective. Again, the only advantage to this is that you get to see the actual names here, all right? If you want a nice handy tool, again, assuming that a person has never done this before, right? Is take one of these horizontal scales, right? And put the abbreviation. So I'm going to put a little m here, right, for meter. And in theory, you could put L for liter or G for gram if you'd like. And then put the smaller units to the right side and the larger units to the left side. So just to make it consistent, I'll use the same colors. So dm would be the next increment over, all right? cm would be the next increment over, and then mm for millimeters would be on the end, right? M&Ms. I wish I had some. Okay. Over here, deca would be DAM, dam. This dam scale. And then hectometers would be HM, and then KM, kilometers. Okay? This would make the idea of converting from one type to another a little bit more intuitive, because the direction in which you're moving your decimal point is more closely implied. All right, so say for example, if you wanted to convert 7 centimeters, right, to so many kilometers, right, you would start here,
It was 938.
and I'll use this green. You would start here, and I'll put a dot here on the centimeter portion here, and then make little jumps basically to where kilometers would be. So that would be 1, 2, 3, 4, 5 in this case. It would be 5 steps, 5 jumps, 5 leaps, whatever you like. So then you take this number 7, and since it's a whole number 7, you would put a decimal point right there. All right. And then you would proceed to do exactly that. Make 7 little waves, all right? Pardon me, 5 little waves. So you go 1, 2, 3, 4, 5. And I'm just going to exaggerate that one. Then fill in the waves with zeros, all right? What are 7 centimeters using kilometers as the unit scale instead? 0.00007 kilometers. And usually for a person, again, who has never seen this before, their mind is usually blown by this, and they go, but wait a minute, how can it change the size of something? Because they look at the decimal and go, that's really puny. And then look at the whole number and go, that's normal size, right? In fact, 7 centimeters is, this is tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. 700 thousandths of a kilometer is the exact same amount of space, distance really, but just using a larger unit. It isn't changing anything except the appearance of it, okay? Anyhow, I'm going to do a bunch of these steps later. Let me finish this drawing, all right? All right. The horizontal scale is the better scale, really. All right, but you need to familiarize yourself with these roots and these prefixes. Right. You can have a decameter, you can have a centigram, right? You can have a kiloliter if necessary, right? Know the abbreviations and know what they represent, right? Now the reason that I left extra space here is just out of maybe curiosity. If you're wondering what are the units that are above, I'll show you, right? I unfortunately have to probably erase something, and I have to zoom out, so humor me for a moment. Here's the whole piece of paper, okay? And at this point, just because I have to fit it in, I'm going to erase this and this, and then just put the abbreviations as I had them. All right, here, as I mentioned, is D for deci, centi, and milli. All right, if you were to go several steps downward, right, it would have to be 3 steps. So I'm just going to put a dot here because there's no name for that, and then a dot here because there's no name for that. And now I'm going to put the next unit would be micro. Now, depending upon who you're talking to, right, micro in sciences is abbreviated by the Greek letter mu, all right, like a cow moo. And it looks like a stylized M, or U rather. So very curvy, something like that, all right. If a letter P and the letter U had a kid, you know, there you have that. Would be mu. Sometimes they use MC instead because maybe it's more intuitive as being micro. It's arguable, all right? If you went down 3 extra steps further, all right, you would get to nano on the 3rd step in terms of size, and that is abbreviated naturally N, all right? And then it's pico, and then femto, and atto, and zepto, which sounds like Marx Brothers, if you were asking me. Every 3rd step, all right? If you went up this way, again, just to fill this in again, deca, dA, hecto, H, and kilo. The unit name exists, again, every 3 steps up now. So dot, dot, and then in the 3rd one, there's another name, all right? Mega is the 1st one. That's for a million, all right? Like the lottery, right? And then another 3 steps up would be giga. It is pronounced giga, not jigga. All right, and it is capital letters in this case. Capital M and capital G. If you went another 3 up, it would be tera. All right, now, in the world of computing, all right, historically, we were on the scale of megabytes in terms of memory, right? Right, and then more recently, it's been like, you know, so many gigabytes, you know, hundreds of gigabytes, but memory capacity in a computer is now approaching terabytes if it hasn't already gotten there, all right? Even as a norm, I'm saying, not just a supercomputer. Anyhow, there's things beyond tera, of course. See if I remember. Peta, exa, zeta, iota, all right? And eventually we'll run out of names, but, and there doesn't seem to be a real system here, except that we use capital letters the further up you go here, all right? And lowercase letters or Greek letters this way, all right? Every 3rd step, all right, has a name. So that's a step and that's a step, okay? And the system would still work. If you wanted to convert millimeters to megameters, right, you're just gonna have a really, really long decimal number, all right? It would still be the same size, but you'd be using a larger unit to express that quantity. Okay. Let me see. Let me give you something else, and then I'll switch slides here and do some examples with you. I put 3 on here, these 3 horizontal scales. Because again, if you wanted to build a reference, which is the whole point of this handout, you might make this as the millimeter scale, this is the liter scale, and this is the gram scale. But again, do exactly the same thing, all right? DM, CM, MM, you know? So this would be DL, CL, ML, milliliters, right? And DG, CG, MG, milligrams as in a vitamin, you know, something like that, tiny, all right? And similarly, label the other side, all right, for the larger units. I should have wrote this in red, really, to be consistent. All right. Let me abbreviate this. I'm going to just turn this off for a moment and finally do some examples with you. Because I'm waking up too. What I'll make available in Canvas is a completed table. If you chances are you may not see this, so you can have that. Right. Again, this is just assuming that you have absolutely no familiarity with the metric system at all, right? Not to insult your intelligence, right? As a teacher, one thing that you have to do is assume that nobody knows anything that you're talking about, right? It is always better to over-explain something than to under-explain it, right? Your job is to make things clear, okay? Never forget that. All right, here are some examples, all right? Let me again confine myself to several spaces here. essentially what you'll be asked to do is to convert,
I could take the social.
right, in several steps, all right, sometimes. You know what, let's do away with that one. It's not even anyway. Okay. So, first one, a question of 473.3 meters, right, is equal to how many km, all right, kilometers. Right. Maybe over here, what I should have done was make myself a little scale to make it easier to do this. So I'm going to draw the scale with 3 increments this way, 3 increments this way. Right? After a while, you don't even need the drawing, you just know. Right? But just to introduce the concept, let me put, since we're talking about meters, that's the base unit, so this is dm, cm, and mm. And this is DAM, HM, and KM. And it works like this. Pay attention to the decimal point. If there is no decimal point given to you, one would always assume it is on the far right, right? But there it is in this problem. We're looking to convert meters to kilometers. So on the scale, all right, put a dot at the location of meters, which would be dead center in this case, all right? And then make so many leaps to the left, because that's where km would be, kilometers. So it'd be 1, 2, 3, right? 3 jumps, okay, that way, right? Then if you have the figure 473.3, right? Make that many waves this way. 1, 2, 3. And then, just to distinguish it from the original point, maybe exaggerate that one. Right? So, 473.3 meters is how many kilometers? 0.4733 kilometers. Right? If you want to be fancy, a lot of times what will occur is there's a 0 here. Right? That's for flair, if you will, for stylistic purposes, aesthetic. Right? It's arguably to make this decimal point easier to see, but you know, that's kind of debatable. Right? So notice the decimal point is 0.4733 kilometers. It is the same exact quantity in reality. Right? 473 meters is quite a lot of meters. Right? That is like on the order, if I would guess, you know, if a football field is how many yards? 100 yards? Right? Is that correct? I believe it is. Right, like 4 football fields, you know, almost 5, right? So this isn't a shorter distance somehow. It is deceptive that way because you're thinking of decimals as being tiny, right? But look at the unit. It's expressing the exact same quantity using a much larger unit. That is why it's a decimal point, not really a whole number anymore, or even part of a whole number.
You could enter as a full amount.
Losing my eyesight here.
Yeah,
Okay. Let's do another. All right. What if you had to convert 14 grams, again, know the abbreviations, to so many CG, which would be centigrams. All right. You could draw yourself a scale, all right, to get familiar. And have 3 increments on this side of the center line and 3 increments on this side. And then put the abbreviations in. So, if we're talking about grams, that is the base unit. G would be in the center, right? And immediately to the right of it would be DG, CG, and MG for milligrams. And then DAG, DAG, right, HG, and KG. Now, incidentally, you might be wondering, do those other units in the middle here, like DAG, get used too often? Not really, no. Right? But they still exist as a concept, and we have to account for them. All right. Anyhow, so similar thing. Where is the decimal point in a whole number like 14? Right? It's really there. So you have to unfortunately draw that. Right? And I'm going to make myself a little space, 14 point here. All right. And then go to grams here and make a dot. All right. So there's a dot here at this location. All right, because that's what we're starting with. All right. Where are you going? To centigrams, which would be to the right of it. How many spaces? 1, 2. 2 jumps. All right. That means that this is, you're going to make 2 waves that way, to the right. 1, 2. And then just to distinguish the original dot from this new one, make that a little bit larger, right? And fill in the void. The reason you draw waves is it's a little pocket, right? Easy to put a 0 in there. So 14 grams is how many centigrams? Turns out it's 1400. Right? You could, in theory, put a comma here, but your textbook will, in the case of 4-digit numbers, not bother. Right? Even though I consider that sloppy personally, this is the way you see it. Right? Maybe it's easy to read. It's, again, debatable. All right, so 1400 centigrams. It is the same exact quantity in terms of grams as for mass, all right? It's just using that, it's just expressing that amount of something using a smaller unit in this case. Smaller units are on the right. Larger units are on the left. Always. Okay? And always the center line would be something like that. Okay? Let's do 2 more of these and then we'll shift gears. Do kilometers to centimeters. This is kind of an odd one. Convert 80 kilometers into so many centimeters. This is not the worst case scenario, but it's going to be pretty drastic. All right. Since we already have the scale for meters here, I'll just erase this one, not to be distracting, and a little bit of work that had been done. And try to restore it a bit. Okay, now, look at where we're starting, a larger unit. Look at where we're going, a significantly smaller unit. So we're not starting from the center in this case. We're starting from all the way over here, right? And we're going there, right? How many spaces is that? 1, 2, 3, 4, 5. So this is 5 jumps, which is equivalent to 5 decimal places towards the right. So you would take your number 80, and a decimal point would be understood as being right there to start with, and then make 8 waves that way. Pardon me, 5 waves. So go 1, 2, 3, 4, 5. Right? And then fill in the void. Each little wave is a little pocket, and you put a 0. Right? So 80 kilometers is how many centimeters? If I'm being traditional here, it would be this. Every 3 in the United States we put a comma, so it would be 8 million. Centimeters, and that's the decimal point that's there. 8 million centimeters is the equivalent of 80 kilometers. All right. Again, it is deceptive, right? If you're unfamiliar, because you go, wow, that's huge, right? Because you're looking at the magnitude of the digits involved, right? Versus 80. But in fact, we're talking about the exact same distance. 80 kilometers is on the order of 80 miles, really. All right, so pretty far, all right? I live in South Amboy, so I mean, like, the distance from here to New York is no more than maybe, I don't know, 30 or 40 miles, something like that. Not even. I mean, technically, Staten Island is. I could spit at Staten Island. It's so close. All right. I won't do that. I swear. All right. I wave at Staten Island. When I was a kid, I used to live in Brooklyn, so I used to wave at Jersey. Anyhow. this is the same distance as 80 kilometers, just expressing that quantity using a very puny unit. And it could get worse than that. You could express the same quantity in millimeters and it would be one extra jump, right? And then you'd have 80 million millimeters and so forth. Here's an example of when you have to compare things, right? And we'll shift gears. If you had to order quantities, right, from smallest to largest. That one is getting dead here. All right, and let's just say that these are the quantities that you have. All right, 3.4 meters, 3,421 millimeters, all right, and 104 centimeters, all right. In order to make a fair comparison, they all have to be the same unit. Now the question is, do we make them all meters? Do you make them all millimeters? Do you make them all centimeters? It isn't wrong if you make them all any one type, right? You could make them all meters if you like. You can make them all centimeters if you like. You can make them all millimeters. I think from experience with doing this that it's probably easier to convert everything to the tiniest unit, all right? So you'll see something very similar. This will be, you know, a magnitude of 1,000, and this will be a magnitude of 1,000, and this will be a magnitude of 1,000. So that's only from having done it that I would, you know, say that. So let's say that we convert, this one is fine the way that it is, right? But let's convert this to so many millimeters, and let's convert this to so many millimeters, all right? If you're going from millimeters, pardon me, if you're going from meters in this case, down and to the left, whichever scale you like, to milli, that's going to be 3 spaces. So after a while, you won't need to draw the picture. What you will do is you will simply make 3 waves, right, in the direction that is appropriate. In which case, this is really 3,400 millimeters, right? And the same thing here. Centi is a little bit higher on the scale, a little bit further to the left, and milli is a little bit further to the right. It's a little bit lower. So you would, and how many spaces apart? 1, all right? So in this instance, you would make just 1 wave, right? And then you would put a 0 in here, and therefore this would be 1040 millimeters, all right? To make it a little bit easier to see, what we're really working with is 3,400, 3,421, and 1,040, right? Millimeters, millimeters, millimeters. And we didn't have to convert that one because it already was, right? Of these, decimal there, 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 we can make a fair comparison now. Which is the smallest of these? This one, because it's 1,000 roughly versus something that is in the 3,000s, right? So maybe put it in the original's presentation. If this is what they gave you, give them back the same thing. So 104 centimeters is that one there, all right? Next one, all right? 3.4 meters, as a matter of fact. 3,400 millimeters, right? That's this one, right? Goes here. And then the actual thing that was given to you in millimeters, 3,421 millimeters is on the very far right, right? That would go there. Now, probably if you're using MyLab, they'll have the 3 text fields that you will enter this, this, and this in sequence. But if you were going to write it physically on a piece of paper, if it's understood that it's already smallest to largest, from least to greatest, you might just use a comma in between them. I think it's a little bit better personally if you do this. Use a less than symbol, right? If this is the smallest, then the arrow points that way, right? If this is the next smallest, then the arrow continues to point that way. Use commas or use these less than symbols. It means the same thing. All right. Although I personally feel this is more sophisticated, but that's just me. Okay. 104, 3.4, 3421. Using the original presentation. All right. Let me give you another diagram. Yeah, I need to do a little stuff areas here. It's faint, but it will do. This marker is dying. A moment of silence for the Expo dry erase marker. And it's going kaputski. Alright, anyhow. Let's call this a diagram of the metric system usages. So metric usages. Okay. Think about small quantities. So let's get that too. Right. Things that are small. Things that are, for lack of a better phrase, medium. You know? And things that are large. It's sort of like you're ordering in the traditional American soda sizes, right? Would you like a small, medium, or large? All right. Well, when we're trying to decide what would the appropriate metric unit be, all right, here's how I would decide that. You know. Things that are tiny, right, when I'm referring to small, things that are tiny or require a precise measurement. Why does green always suck so bad? I need to write a letter to Expo. Right. Tiny, precise. Let me move the curtains. I don't think we can be able to read that. There we go. Hopefully that's a little bit better. Things that are tiny and require a precise measurement, let's just regard them as small. Alright, this would be appropriately using millimeters. Or milliliters, or milligrams. Right. An example for these would be something like, if we're talking about milligrams, you know, think of a vitamin. You know, a vitamin often has mg written right on it, all right, and then the number 500 milligrams or what have you. It's tiny, you know. A millimeter is something like the diameter of a coin. Right, and milliliters would be something like NyQuil. Yeah, if you've ever taken NyQuil, fine product, by the way. It comes with a little shot glass, all right, that is incremented in milliliters because you don't want to OD on NyQuil, naturally. Right, don't do that. All right. Put that in there. Now, for medium-sized things, which maybe I use this phrase, things that are macroscopic. And macroscopic is things that are more or less terrestrial, that they're not difficult to see them, right? But not necessarily large either, right? The appropriate units would be the base units, meters, liters, or grams.
You take it in.
Right. All right.
Is it
What would be examples? A person's height, right, is something that is easily discernible. You know, at least not too far away from them. You know, something like a bottle of soda. Again, not to wear it out. Right, but a bottle of soda, we're all familiar with, no matter where you live on the earth, right, is in liters, right? Years ago, when I was a kid, believe it or not, they used to sell soda in a 3-liter bottle, which is like, you know, embarrassingly American, you know, because it's such a large quantity of something like, I need a vat of soda, all right? And imagine drinking the whole thing, it'd be bouncing off the walls. All right, it's not good. All right, now more or less nowadays it's like 2 liters, you know, family size, you know, as opposed to Jugunda. All right, and don't drink soda, all right, or at least only save it for this occasion. All right, it's very bad for you. All right, grams, something like the mass of a food, something that you're ingesting that is a solid. All right. Right, is usually on the order of so many grams. Like if you've ever had, like, you know, you're making a smoothie or something, or some kind of like powdered drink, Nesquik, if you will. All right, usually, you know, it can be measured in grams. All right, it'd be funny if it was kilograms of Nesquik that you were drinking. All right, imagine that, a whole pallet. All right, the movie Dune is in my chocolatey drink. All right, all right. Yeah, when you think of grams, maybe think cereal. Right, breakfast cereal. Okay, now as far as large things are concerned, this is just to give you a feel again. They're still technically macroscopic, but I would say big, you know, but not easy to see entirely. Right. You know, for example, kilometers is a large thing, right? You can't, as a human standing on the earth, you know, see the distance that is 1 kilometer pretty easily, at least not to distinguish it from anything else. Yeah, again, the units that would be appropriate would be something like kilometers, kilometers, right? Kiloliters, right, which is less commonly used, I suppose, and kilograms, which is common. You know. As a matter of fact, I would say the kilogram is the actual SI unit of choice when it comes to masses, not grams, but so be it. There is actually another one that I'm going to mention in a moment, but let me give you some examples of these. All right, if meters is appropriate to a person's height generally, right? There are not too many people who are 2 inches tall, you know. Kilograms is the large size, which is, again, it's not easy to decide somebody's mass, per se. Is actually significantly larger. So, let's see. A person's weight would be appropriate here. Right. You would measure in kilograms. Right. Kiloliters, industrial liquids, I would say. Industrial liquids, like petroleum. In the United States, we just usually refer to petroleum as gasoline, all right, or rather oil, I should say. But if you in New Jersey, where I live, there are plenty of oil refineries, right? Yeah. And that have vast cylindrical tanks that they store probably petroleum, if not some other industrial liquid, for refining. All right, I would bet that they're probably measured in kiloliters because they're engineers, you know, and scientists that work there. Anyhow, kilometers would be distances between two places, naturally. Vast distance.
Right.
Okay. Now, before I switch out of here, there is something else. Now, remember, a kilometer is a measure of one-dimensional distance, really. All right, a length. All right. I'm going to put a little asterisk up here. All right. When we're talking area, all right, 2 dimensions versus this is 1-dimensional measurement, something that is 2D, there is another unit that gets used, which is called a hectare. And since we're already familiar with the concept of a hectometer, right, as a possible thing, a hectare is basically on the order of an acre. What we think of as being an acre in the United States, a unit of property, of house property.
I've heard people like figuring out
House lands, just to make it fit, you know. Right. A hectare is something that you have as an alternative, right, to use. That would technically be a metric unit, right? Right. I'm using the similarity symbol because they're not really the same thing, right? Again, we're familiar with acres here, but a hectare would be the equivalent, right? The equivalent in its appropriateness. Let me give you a couple of conversion factors, just in case. Right? You could look this up, of course, but I'll show you how these things are related now that I've mentioned it. One hectare is about equal to 2.5 acres. Right. And at the same time, 1 square mile, meaning literally it's square, miles times miles, is, that's MI with a little 2, right, is about 260 hectares. Right. Lastly, 1 acre is equal to exactly 1/640th of a mile, right? Which as a decimal would be this, 0.0015625. I believe it terminates miles, right? 1 divided by 640 is that decimal. 0.0015625. That looks like it terminates to me. 1 acre, that is equal to that. 1 square mile is that so many hectares. A hectare is 2.5 acres if you're interested. Okay, so what was the purpose of this diagram? To kind of give, again, assuming that you are unfamiliar with the metric system and where it would be appropriate to use it, right? Kind of, this is my idea of insinuating, well, that's a large thing, so you would use this unit, and this is a small thing, it would be more appropriate to use this other unit, right? I think probably the most practical one would be person's height, meters, you know, so if you're 6 feet tall, about 1.8 meters, all right? If you are talking about a person's weight, though, kilograms, right? All right, let's do some examples. Again, example. Convert the following. 1 square mile to so many square centimeters. Right? Often this is spelled just out, literally square miles. It means miles times miles, so just understand that if you see the word square, it means miles, which is abbreviated MI here, with a little superscript of 2. Right? So the question is basically, 1 mile squared is equal to how many centimeters squared? Is that? No, meters, sorry. I'm sorry, I can't see today. What the hell's wrong with you? 1 square meter. Alright. Here, I'll spare myself the trouble here. M meters. Alright. Squared. Right. Convert 1 meter squared into so many centimeters squared. Alright, a little more concisely. 1 meter squared is equal to so many centimeters squared. Sorry for the hiccup for the 1,000th time today. Alright. That's what you have. This is what you want. Alright. I'm going to draw a picture because I want you to see something. Right? And I would encourage you to do this every time this kind of question comes up. Literally draw a square. Okay? Literally draw squares. Right? This is a little teeny tiny square. Alright, and although it's not really it's not in proportion to what it should be, just to give you a feel, alright? If I'm talking about something that is an area, and this implies an area, alright, then it is appropriate to draw a little square, right? And I'm going to label it like so, right? If it's truly a square, it would have to be the same dimensions on 2 different sides. Alright, so let's just say that this would be 1 centimeter this way and 1 centimeter this way. And you know that the area would just be these 2 things multiplied. Alright, it would be 1 times 1, which is just 1, and centimeters times centimeters would be centimeters squared. That's the area, that is the inside of this. Now again, it's not going to be proportionate, but let's say I drew a much larger square adjacent to it. And again, I do this myself every single time just to kind of get myself comfortable. Right? Not to scale, of course. If this is truly a square, then again, the same must be true for it. All right? The dimensions of the sides would have to be the same, right? If it's 1 square meter, it would be meter this way, 1, and 1 meter this way. Now the question really is, if I converted from meters squared to centimeters squared, right? How many, what would that number be? Don't jump the gun, right? You might think to yourself, well, I'll whip out the scale that Dodo here told me, right, and proceed to use the scale, which I would encourage you to use it, but not yet, all right? In other words, you might go, well, ding dong, you just told me that I could use this scale and I'm going to convert from meters to centimeters. You will do that eventually, but what you want to do to avoid a mistake is do it in the basic 1 dimension each, right? You might have it memorized, right? But if you don't, yes, build the scale. Use meters, right? And then 2 increments away is centimeters. So if I convert each of these parts first, that would be to my advantage. I won't make a mistake, right? I'm just going to start here and then go here. 1, 2, right? 2 steps, 2 jumps. So what does that mean, right? If it's hole number 1, and I'm converting to the small unit this way, make two waves. 1, 2, fill in the gap. This is 100 centimeters. 1 meter is 100 centimeters. That's the definition of it. All right? Well, not the physical definition of it, but as in physics. All right? But it is literally that on a ruler. Okay? So, if an area is these two dimensions multiplied, a length and a width, if you will. If it's 1 to 1, that isn't changing anything, right? 1 times 1 is 1. But if you're trying to convert to square centimeters, you have to change the individual side lengths, convert those, all right? And then multiply, all right? In other words, multiply last, all right? So what is the area then? It's not 1 times 1 unless we're sticking with meters. It's actually 100 times 100 is what I'm getting at. So what is 100 times 100? The number of zeros is the answer, right? Basically, right? It turns out that this is 10,000
Is he giving you an option?
centimeters squared, okay? Because if you're converting it to centimeters squared, you got to have this as centimeters and that as centimeters first. Then you multiply, all right? And then the units are centimeters times centimeters abbreviated as centimeters squared too. Also, all right? So do that. Do your multiplication last, convert first. Convert the parts. Sorry for the sloppiness. Convert the individual side dimensions, the parts, if you will, first, and then multiply because that's what area would be. Okay. All right, just beware of that. All right. Let me give you another diagram to summarize. Blue writes well again. Don't go away. Yeah, just to speed things up. There are some formulas that would be good to know. As you go through this. The formula for area, formulas for areas, and then formulas for volumes. Okay, again, convince yourself, all right, areas are two-dimensional, 2D. Volumes are three-dimensional, 3D. They're real, right? These are virtual usually. All right, if you see the word surface in context, you're probably talking about an area. All right, well, similarly, if you see the word plane, insane in the membrane, insane in the plane. All right, that's probably an area. All right, the word space, even though we will talk about, hey, you want me to figure out the area, you want me to get the inside space, people go, yeah, in ordinary conversation. Reserve the word space for really speaking about volumes, because that is really more correct. Again, English is a little complicated. We have a lot of choices, synonymous words to choose from. All right, but surface officially is referring to area, and space is referring to volume. Okay, space. right? Or alternatively, capacity. Right. 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 Now, let me put a little thought cloud up here. Remember, everything stems from the basic concept. So here's a little thought cloud. We have this concept of distance we've discussed, right? And distance is really one-dimensional. It is the foundation of these subsequent ideas. Right. Hopefully that glare is not too horrifying. I think I should aim this a little bit higher. Oh, I can't. How about that? Okay. Distance is a one-dimensional concept, right? And there again, we have a lot of alternative phrases to choose from. When you're speaking of distance, it's usually more appropriate to speak about, use that word when you're talking about places, you know, locations, right? But it is an example of a length. Right? And a length is alternatively a width, right, or a height, or a depth, or if you want to be very general, a side. That's the most general way of talking about something. In the formulas, very often there are abbreviations for length, width, and height, right? Especially when you get to volume, right? But just realize these are synonymous. They're all the same type of thing. They're just being used to distinguish one number from another, okay? So the formulas that would probably be practical to know here would be these, all right? There's area of a square or a rectangle. So I'm just going to abbreviate this as rect, all right, or SQ for square. A, capital A for areas, all right? It's just two things multiplied, right? But what are those two things, all right? Well, if you're talking about a rectangle, it would be appropriate to use L and W, right? They're the same type of thing. They're sides of a square, right? Or sides of a rectangle. But we use these two words instead because they're not the same number. If we were talking about a literal square, all right, then you might call this S times S, right? That's an alternative. Anyhow, just knowing that it's two things multiplied together will get you pretty far. If you're talking about essentially a three-dimensional area, which is a volume more appropriately, right, then the formula has a third dimension that you multiply by. So it would be V, and you would use this for either a cube, officially, or you might call it a rectangular solid, right? And the formula would be three things multiplied. Right? There's still those dimensions that would be an area, but it would be a length, a width, and very often they use the letter H. I'll use a lowercase h for height, right? So sometimes they write them in script. So areas are two things multiplied, volumes are essentially three things multiplied. And we only use these different words to describe sides when we're talking about something that is really a rectangle, right? Rather than a square per se. The volume formula for a cube would be side times side times side, because there's no reason to have to change the labels. They're all the same dimension anyhow. Okay? In addition, I need the space, so I'm just going to erase this up here. It's still area. Another formula that would be good to know would be the formula for the area of a circle. So I'm going to make a little label subscript circle here. That is famously pi times the radius squared. Right? When you're performing the calculation, certainly use your calculator because you can get very high degree of precision for pi. You must do the squaring portion of this first. Right? If they don't give you a radius, which is what the R stands for, right? If instead they give you a diameter, there's an alternative formula that you could finagle, which is this. pi times diameter divided by 2 squared. I'm putting this in parentheses because you really would have to do this division first, right? Then square, then multiply by pi. You follow the order of operations when you're dealing with these formulas, all right? Now, because I'm a little concerned, all right, remember what these actually look like. All right, if you have a circle, not the best drawn circle, from the center to the edge is a radius. Right? All the way across the center is a diameter. So you will have to, they may verbally just tell you what the numbers are, say that this is a diameter, say that this is a radius. But, all right, if they give you just a drawing, all right, and tell you to compute the area, all right, remember halfway is a radius, all right. This is half a diameter. Right. Or you might say a diameter from this perspective is 2 radii. Okay. This is really the subject of chapter 8, but there were some problems that they gave you these and they kind of made the assumption, which I don't think they ever should. They're like, oh, yeah, you know these things. All right. You probably do, all right, because you're 20-something years old or what have you, all right, or maybe a little bit younger, all right. But if you're watching this, you probably have seen area formulas. Nonetheless, as a teacher, you will be remiss if you don't explain these things, all right. So anyhow, depending upon what you are working with, if you're given a diameter, divide by 2 first, then square, then multiply. Otherwise, you square your radius given to you, and then you multiply by pi. Side note, all right? Pi, what is pi? Well, it's an irrational number, famously, which means that it is infinitely stretching, and you can't possibly see or use all of it. But your calculator has a pi button. So when you're using your calculator, I would press this button. If you're just doing this by hand, in theory, you can get away with using the first 3 digits, right? On a calculator like this type, right, that is required for the class really, there is in fact a pi button. So it's a little dark in here, but if you turn it on, Ziegler, clear. If you press pi and then enter, it'll show you a high degree of precision here. Right. Pi to several places, 10 digits maybe. Realistically, if you're just doing the calculations by hand, you would use 3.14. But if you happen to have a calculator, and a scientific calculator specifically has pi, all right, use it. All right. There is another formula for volume that may come up in your MyLab stuff. They don't give it to you. You could always look it up. I mean, don't be afraid to do that, of course. All right. But the volume of a cylinder, as long as you recognize the shape of the cylinder, a cube, of course, looks like this. All right. A 3-dimensional square. All right. A rectangular solid would just be a little bit more exaggerated, but it's the same concept. 3 distinct dimensions in this case. Side, 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 length with height. They're the same concept. All right. A cylinder, the volume formula is pi times, I'm going to use dots in this case, r squared times height. All right. Now, inside this is this concept. Right? Remember, this much of the volume formula for a cube or a rectangular solid incorporates area, right? A cylinder incorporates area as well, but it's the area of a certain layer that happens to be a circle. Right? Think of it as like a stack of pancakes. Right? That's a cylinder, essentially, right? It's an infinite stack of pancakes. right? Thinner and thinner pancakes, if you will. So the dimension would include a radius at some point and how tall it is, how many pancakes really is the number of layers, that's the height. This is a little bit finer of a drawing, I hope. But you get the idea. All right. So, just like you need a third dimension to get volume, right? To translate area into a volume is times an extra number. Well, you take the area formula of a circle because that's what the layers are built of, right? Times the height dimension. That is essentially how many pancakes there are. I'm getting hungry. Can you tell? Let me give you an example, and then again, we're going to shift gears. All right. Let me put the other light on. Say you had to find the area of this circle, and they're telling you that they're just drawing that, very nonverbal, right? They give you this dimension measurement as being 76 centimeters. And that's the center. You have to ask yourself every time, is this a diameter, all right, or is this given drawing a radius? If they don't explicitly say it to you in the instructions, right? If they just give you a picture and you see a dot here, right, and there's a line that goes across, it might be dashed sometimes. What are you actually working with, a diameter or a radius in this particular case? Of these two things, it's probably a diameter, right? Therefore, if you're going to find the area, the appropriate incarnation of the area of a circle formula is pi times the diameter divided by 2, and then squared. Right. Use your calculator when you're doing this, right? You don't have to rearrange anything algebraically first, all right? Insert the figure where it is appropriate. Since we've identified this as a diameter, let's put 76 in here, okay? Follow the order of operations. All right. Specifically. Why? You might say, well, it's an equation. That's true, but you're not looking at anything but just the right side, right? It's going to spit out something for the left, all right? But there's no rearranging stuff, right? So you just have to insert, substitute. So follow the order of operations to simplify it. You should do this division first because there is a parentheses here, all right? So what is half of 76, right? Essentially, that's pi times 38, and since the unit is centimeters, it's 38 centimeters squared, right? How come? Because half of 7 is roughly 3.5. Well, it's exactly 3.5. So 3, and then a little 1 left over, and 2 goes into 16 8 times. Okay? Right? Then you square. If at this point, right, you want to use your calculator, because again, you have a high degree of precision for pi, that's cool, right? But just be extra anal retentive, careful, all right, how you enter it, right? There are these parentheses here, all right, if you want to say, this is the thing that the calculator needs to do first, all right? And there's a button here that is called caret. This is an upward pointing arrow here that will allow you to put in an exponent of whatever you choose, right? So if you, basically in sequence, type this, right, pi, that button, multiplication times, make sure that you use the parentheses button, then 38, then close it with the other parentheses, all right? And then use your caret, and then use 2. That should be okay, right? The calculator should understand, only for the reason that you put this in here, that this is where this should be dealt with first. As a matter of fact, if you want to be extra careful, you could just say, put this inside the parentheses. Let me see if I can get away with it. The reason that I'm precautious is that calculators are great, but they're not always so great about the order of operations, so you have to be careful. I tend to do a lot of this by hand, but to avoid a round-off error mid-calculation, you might set it up appropriately. So let me see if I can get away with what I've just said here. Times 38, 2, right? Essentially, I have typed this, right? And that is correct, but we'll see if the calculator really knows, right? If that is appropriate. And let's see. Yes, it's good, right? You get this decimal number, right? 4,536.459 and so forth, right? So cool, all right? All right, all right. Be careful, all right? What you end up with is that the area is equal to 4536.459, and then there's some stuff that trails it, right? The instructions I have given you have not told you to specify anything. If we were following significant digits, we probably would have went with 2, right? In which case this would be 4,500. But let's just say that we're going to round it to the hundredths place, right? So based upon 9 here, this would be approximately 4,536.46, and then there's the unit. Remember that centimeters, this superscript of 2 does not just affect the digits, it affects the unit. So it would be centimeters times centimeters, and this is therefore appropriately an area. Centimeters squared implies an area. Okay? 4536.46. Let me give you another quick diagram and a little bit of information, and we'll move on.
I don't know if the stimulus went out because it's an odd number. I don't think it was the stimulus. Usually, I think the next one is supposed to be 1,400, but I don't know if they agreed on it yet. Anyhow, your individual savings is $2,000.
There will be a situation where you have to decide between the unit for volume,
It's okay. No, it's okay. It's 2,800.
which pertains to solids
47 cents.
or gases,
Yes. Yes.
or those that are for liquids. This is really what I was alluding to before. All right. The SI unit for volume is usually liter, right? That's the base unit, really. All right. L. All right. So you would see L or milliliter, probably, because those are the two that are the most practical. All right, especially in the chemistry class, right? Milliliters. If you could express something that is a liquid using these units instead, right? But just to distinguish them, what do they look like? If you're talking about the volume of a solid, again, very often it's meter times meter times meter. So you might see meters cubed or centimeters cubed. It is implying, essentially, when you see something like this or this, that you're dealing with the volume of a solid or gas, maybe, right? Rather than the volume of a liquid, which would pretty much automatically be liters. All right, so just be aware of that. All right. What is a superscript of 3? Cubic. All right. If you see cubic centimeters,
Yes.
there's an abbreviation, it turns out, for that as well.
Your savings has 1,000.
That's cc's. A lot of times you'll see.
47 cents.
People who are into just like automotives, like motorcycles and stuff like that. Even Mario Kart, I want to say that they described one of the races using cc, right? It means cubic centimeters in math, right? Anyhow, or if you've ever watched any of those, medical programs, right? The doctor always comes in, or the nurse comes in, and they're like, I want 12 cc stat, and then it's supposed to give somebody an injection of some sort. All right. Anyhow, just realize that that's what they're referring to. Math speak would be like, oh, you mean you want cubic centimeters? Okay. It's the same thing. All right. All right. Now, fun factoid here. And I think I have it posted on this in your packet too. So let me just flip a little bit and show you. Yes. All right. There's a diagram in your packet. All right. That is the information I'm about to give you. 1 cubic centimeter is equal to 1 milliliter, and that's the script they use instead, and 1 gram, right? This comes from the definition of the volume of 1 liter, all right? And the way that it breaks down is like that, right? You can convert, it's actually a real convenience. What's my place? All right. 1 milliliter can be converted to easily and directly and not without lying at all 1 cubic centimeter. And similarly, 1 gram. 1 cc. Right? Beware of that. Right? Also, technically, 1 standard full-size liter is the equivalent of 1 cubic decimeter, technically. Right? And that would be 1,000 cubic centimeters. Okay. This may be useful to you as conversion factors. All right. Anyhow, you have the much of the same information again on this sheet, right down here, and incorporating this to a degree. Your joint account with Daisy does not have anything coming in. All right. Let me do an example of conversion now. We were at 2 hours now. Okay. Your deposit went to your individual savings. All right. That was the 26th of February. All right. We're going to convert 3 cc's. We're all medical practitioners into so many milliliters. All right. I want to remind you of something too. I included this, and you don't have to do it, but when we get to section 7.4, we're going to really need to. This is a model of a way to convert from whatever is given to you to the thing that you desire, right? By way of what is known as a conversion factor. A conversion factor is, for all intents and purposes, a glorified fraction. You start with something like this, maybe, 2 at a time, but you write it in the style of a fraction. And you decide its orientation of what is on top and what is on bottom. I look like I'm doing some kind of voodoo shtick here. Hocus. You decide the orientation of the 2 figures that you see here and here at a time, or 2 figures here and here that you see at a time, by way of what you want and what you're given. Right? You basically are strategically arranging something to cancel. Right? So let me explain this. Right, and we're going to come back to it when we do section 7.4. It would be appropriate maybe to use here. All right, here's a model for conversion. Right, this is going to be a little overkill in this case, but I want to broach the subject at least because I need to talk about it later. Whatever you are given, right, you can multiply by the appropriate conversion factor, which is going to be in the style of a fraction, basically. All right. And that, if you rig it correctly, will spit out what you want. So in this particular case, we're given this 3 cc, all right, as a unit. If what I want is so many milliliters, then I need to arrange a conversion factor with the numbers arranged on top or bottom in a certain orientation, so that there's going to cancel this unit, and it's going to leave me with that unit. Now, it just so happens that I have a conversion factor here. It's just not written in the style of a fraction, right? Nonetheless, 1 milliliter is 1 cc, right? By way of cubic centimeters. So, if I want to cancel out cc's, where would it be appropriate to put cc's in relation to this line? On the bottom, all right? So I'm going to put cc down here, and what am I looking to end up with? Milliliters up here, all right? Then I put in the numbers that are related. It turns out that it's 1 to 1 exactly, so it's not going to really matter in this case. But it would validate whatever suspicion you have, right? And it's a thought process that eventually becomes rote. Once you get comfortable with this, right, you'll go, you don't think too hard, you'll just get it correct, right? You'll go, this is intentionally written down here for this purpose, to cancel the unit and leave me with the unit that I want. Now it's just a matter of combining the numbers that are adjacent to them. It would be, if it's in the style of a fraction, top times top, numerator times numerator, in which case you just have 3. All right, and technically bottom times bottom, in which case you'd have 1. That 1 is superfluous though, right? So this is really just 3 milliliters, right? If you intuitively know at this point that it's 1 to 1, so there's really not much thinking involved in it, cool, all right? Don't fight your intuition, it's a blessing, I always tell people, all right? But just realize that we're gonna need a system for something that is less intuitive to us. So I'm bringing it up again now. I think I mentioned it maybe a couple of weeks ago vaguely, all right, because it's going to be imperative soon. Okay? Now let's do a volume problem. And I'll again illustrate a cylinder. So, suppose you're given this question. What is the capacity of this, and I'll draw it, a cylinder in liters specifically? Now I'm going to fill in some information in the drawing, and you'll have to decide what the parts represent. So here's the center dot here, and we're going to the outer edge, and the number that should be written there would be 50 centimeters. And then simultaneously, there's a dimension this way, which is 148 centimeters, right? Now, what this picture is supposed to represent, apparently, is a hot water heater. Stole this from the textbook. All right. We have to decide, first of all, if it's not explicitly stated. I already said what it is, but if you look at a drawing, you can tell what shape it is, at least if it's drawn well enough. So, what shape is this? A hot water heater is basically a cylinder, right? And if we're talking about capacity, what concept are we really speaking of? Volume. So without it being explicitly stated, we need to find the volume of a cylinder. And we have a formula for that. The volume of a cylinder is the area of a circle, essentially, times an added dimension. The added dimension is a height. Right? Now, even if we don't immediately multiply something, let's just figure out whether we have the appropriate information in the drawing. First of all, we would need a radius, right? What is this dimension? That's a radius, we can say for sure, because it goes from the center to the edge of the circle. It's at an angle that you're looking at it, so it looks like an oval, right? If you were looking at it straight down, it would be a perfect circle in theory, right? So this is where 50 would go, right? And this dimension this way, which is a stack of pancakes, if you will, right, which gives it, you know, it's what makes it real. It gives it a thickness, all right, is the height dimension. So these units, however, are centimeters and centimeters, right? So I'm just going to put in the numbers right now and then the unit just underneath them, all right? Is it wrong, all right, to do the straightforward, like you could type this into your calculator as long as it gets the order of operations correct, right? I'm going to erase this parentheses now because it isn't actually part of the formula. I only did that to isolate the fact that this is an area by itself, and that makes it a volume. Anyhow, you would have to multiply, naturally, these quantities in sequence. The one that would have to get done first is actually the thing that is with the square here. All right, that would make it centimeters squared, and then centimeters squared times an extra centimeters would be centimeters cubed, hence it's a volume. All right, but here's the issue. They want this to be in liters, right? So you can convert the units before or after you multiply by pi, but maybe we'll do ourselves a little favor here. We have some information already, all right? That 1 millimeter is already equal to 1 cubic centimeter, all right? So what I would do is, before you introduce pi, all right, do the arithmetic that is squaring and then multiplying by 148. Remember, since the rest of this is just multiplication, legally speaking, it's commutative, which means that you could arrange the parts in any order that you want. I know that in a textbook that comes first, but it's not imperative that it is multiplied first. We're going to kind of reserve that just because it's an irrational number. I'm being strategic is what I'm getting at. Anyhow, 50 squared would be 5 times 5 with 2 extra zeros, so that would be 2,500. Centimeters squared would be centimeters squared. And then there would be this additional 148 with a centimeter attached to it, right? The reason that I'm just paying attention to these numbers portion of this rather than 3.14, the pi thing, is because this is going to be a terminating decimal, a terminating number, probably a whole number, all right? And it's going to be in the unit of centimeters cubed. I'm going to then maybe convert that to milliliters and then to liters if necessary. I could also incorporate this other conversion factor if necessary, all right? Anyhow, if you took your calculator and you multiplied 2,500 times 148, what would you actually get? 370,000. Having done this, you get this. 370,000, right? And because it's centimeters squared times centimeters to the first degree, you add the exponents, you would end up with centimeters cubed, so exponent of 3, right? There is still this pi here, right? Because again, pi is an irrational number, and ideally, you don't want to have to round until dead last, all right? I would not make this 3.14. I would use a calculator because you have a higher degree of precision, right? And round dead last, right? You don't want to round in the middle. You get a less precise answer, a less accurate answer. Okay? Now, who is calling me? I don't know that number. It's probably my car warranty. For my 20-year-old car. That makes perfect sense. Now shut up, you. Thank you. All right, see, it does exactly what I wanted to. All right. Zing. Sorry. Focus, Ziegler. Here you go. I'm going to convert this just to apply pi dead last. Liters, right? And in order to accomplish that, I'm going to, again, draw you that little model that I have for converting from one type of unit to another. I need the space, so I'm going to erase this. All right? Here's the model for converting. All right? What you are given multiplied by the appropriate conversion factor, and sometimes it might be several. In this case, I believe we will just get away with 1. That'll spit out what we want. Right? I need a little bit of space, so this will go away too. Right? What do we want? Right? We want a unit that is in liters, full-size liters. And what we're given at this point is technically cubic centimeters. How many cubic centimeters? Apparently 370,000. Okay, so do I have a conversion factor that will translate this unit into that unit? You do, actually. It's just a little disguised, right? It's written horizontally with something in between, but there you have it, you know. Now what you need to do is just arrange it in the style of a fraction, right? A ratio of one to the other. It's a rate, basically. It converts one unit into another, all right? It's a ratio, which is a fancy way of, well, it's actually the more general way of referring to a fraction. So if I want that to cancel cubic centimeters, I would have to put this down here. And if I want units of liters to appear, I would have to put it on top. That ultimately decides where the number 1 and the number 1,000 goes, right? So you would put a 1 here, and you would put 1,000 down here. Now again, you might not immediately know what the advantage to writing this would be, but I'll show you now. All right. If you disguise this as a fraction by sticking a 1 under it, you know that you could do top times top, you get a number, and bottom times bottom and get a number, and there's no sin in that, all right? But if you're a little strategic and you're patient, you could take advantage of some shortcuts. This is a nice round number, 1,000, right? And this is a nice round number as well. It just so happens that in the same way that centimeters would cancel centimeters here, cubic, all right, which is really the objective, we can do something similar with the numbers themselves. If you see 1,000 here, 3 zeros, you can knock off 3 zeros from here. And that means you got 1 times 1 would be 1 on the bottom left over. And 370 times 1 would be 370, right? Now that's not the answer, but that's what this figure would be in the unit that they're demanding it be. Okay, so the bottom line is this. You're going to convert this unit, cubic centimeters, at some point to liters. I like to do it before I introduce pi, and I know that I can. Now, with your calculator, you would hit the pi button times 370, right? If you feel a little sketchy about this, again, don't feel bad. What you would end up with over here would be 3,700 on the top and 1,000 on the bottom. And you can enter this into your calculator, but the effect is that pairs of zeros would go away, and you'd just be left with those figures anyhow. That happens every time, right? Eventually, you develop a level of comfort with mathematics. This is the goal for all humans, all right? So you end up being more strategic, all right? But the only way that you get there is by doing it a lot, all right? So don't let anyone talk you out of it. And don't talk your own students out of it either. Don't say, I don't do that, it's old-fashioned. You need the experience, all right? This ends up being this volume, I'm going to round it, 1,162.4, right, liters, right? At this point, you could have left it in cubic centimeters and multiplied by pi, but again, it's not the unit that is requested. And there is, in fact, a conversion factor. These, although they're written funny, are conversion factors disguised, right? This entire sheet that I had mentioned earlier, right? They're not written in the style of a fraction, any of them, but every last one of these can be written like a ratio, that is a top sitting on top of a bottom, right? 12 inches over 1 foot. Or if it's a convenience for you, 1 foot over 12 inches. That's the beauty of it. If you've ever taken a chemistry class, you do this a lot. They call it stoichiometry, right? Converting from one unit to another. It's an invaluable skill. right? And the irony for me is that it's only the chemists that were my professors and my teachers in my life that really taught this, right? It's such a beautiful, simple thing when you get comfortable with it. You go, oh man, why didn't they do this a long time ago? I don't know. I wish they did, so I try to propagate that, right? Right? You should too, right? At least if you get comfortable with it. Okay, now we're going to do section 7.3. Oh boy. I guess that phone call wasn't too important. Because I didn't even leave a voicemail. It's noon. Church bells are ringing. Okay, this is technically 7.3. Let me do you a diagram here. We're going to be talking about mass, right, versus weight, as these get confused often. Okay. As I mentioned, the real difference between them is this. All right, mass is constant. Right, it does not vary with location. Okay, whereas weight technically does. Right, weight depends upon gravity, all right, and therefore varies with proximity to the center of the Earth, or whatever planet that you're on, all right? Right, famously in 1969, and thereafter immediately, right, when the astronauts went to the moon, right, they did a lot of experiments naturally to verify things that had only been predicted to that point. All right, they experienced not weightlessness on the moon, but a weight loss, if you will. All right, so they could the footage you've ever seen of the astronauts on the moon, right? They're always like jumping higher than they normally would because they still had the same physical strength that they came from the Earth with, you know. But they're on a plane of existence where the conditions are less harsh in terms of gravity. Right, the gravity of the moon is 1/6 that of Earth. The gravitational pull on the moon is 1/6 that of Earth. Right, which makes it easier to, basically perform athletically, right? The Mars, I mean, the next project for NASA at least is they were going to Mars. Mars, being less massive than the Earth, has less gravity as well, right? It has 1/3, right? The gravity, the gravitational pull, right? So if you went to the moon, you would weigh less. If you went to Mars, you would weigh less. But the one thing that would be the same in all three places would be your mass, right? Mass is a measure of how much matter you're made of, technically, right? So the amount of matter that you're made of if it varies at all, it varies because you've ingested something, or you have thrown up in some way, right? When you lose mass somehow, right? If you go on a diet, right? and I've been on many diets in my life, you lose weight by breathing, actually, right? If you weigh yourself in the morning, all right, your weight will go down, but that's because of your mass diminishing, right? From exercise, right? Right. When you exercise naturally, what do? You exhale a lot, right? Well, some of your carbon, right, some of the matter that you're made of gets expelled a little bit faster, all right, when you're exercising, right? It comes out through your breath, right? Anyhow, let me add to this, all right? These things are not the same, all right? Mass is not weight, right? But these are proportionate. All right, which means that one depends upon the other. One is affected by the other. All right. The formula, if you take a physics class, that they would teach you is that force is equal to mass m times acceleration. If you're specifically referring to the force of weight, and weight is a force, all right, it would be mass times gravitational acceleration. All right, so 9.8 meters per second squared. All right, the one thing that would be the same would be the masses. All right, whether you're referring to it this way or this way, weight. All right, as you can see, weight is dependent upon mass and gravity. All right, so essentially, the more mass, the more weight. Right? The less mass, the less weight. Okay, but that's only because of this relationship. Right? It depends upon gravity, the gravitational pull of whatever you're standing on, right? And it would vary with proximity to the center of, say, the Earth, for example, because that's normal for us, right? In theory, if you were standing on a very high mountain, you would probably weigh a little bit less. You'd notice it at that point. All right. Here are some fun facts, if you want to keep them. Let me put this over here because I need the space. Again, oh, it's my landlord. Pardon me, humor me. I may have to get an electrician to come in. Hello? I'm teaching. What's up? Yeah. No. All right, I'll let him in. It's not a problem. Birdie, okay. All right, he's by the, he's in the cellar, basically? All right, I'll talk to him. All right, don't mention it. All right. I'm not turning off my camera because I want to finish this and I don't want to edit video, so skip this part. I have to let an electrician in to fix something. So pardon me 1 moment. Let me get a mask.
And this, I'm looking at the caller ID. Is this Patricia? Okay.
Keys. I'm sorry, as I mentioned, I gotta let my electrician in, so just scroll through this and I'll be back in about 10 minutes probably.
question, don't mind me. So let me. Okay, this way. And let me know when you're in as well. Okay, great. Okay, great. So you could see your Aspire accounts, all the account summary and everything, right? Okay. So on the very top, there's some buttons. There's My Accounts, there's ePower Plus, and there's Move Money. So Move Money is the one you want to go to. And then when you could hover over, it should bring up bank-to-bank transfers. It should be the fourth option down. You got it. Yep. So you could click. So you could click on that, and then you could enter in the amount. Sorry. You there, Bill? You there? You're on the bank to bank part, right? Great. Okay. So if you could add a new account, there's probably a button right underneath. It should be in blue. Add a new account. That would just require the other bank's information. So it will likely ask for an account number from the other institution and a routing number. service will provide a code. Okay.
Yeah, they said a key maybe it's for that door. I thought it was for that, I was trying to open the door and I couldn't open it.
Mal,
Yeah.
the electrician is here. Could he come in?
Hello. Okay, Bob, listen here.
I'm on the phone with someone, they put me on hold, so it's okay, you can come in. Long story short, this outlet inexplicably stopped working. I don't know why, but it was connecting my TV and game, so that was the only thing wrong, so I don't know what happened. We tried playing with the circuit breaker, right? Those switches.
I just checked it.
Yeah, they didn't,
Switches were
there was nothing wrong with it.
Yeah, as a matter of fact, he just checked them in the little phone.
Mm-hmm. Perfect, okay, I'm glad it's set up like that.
What's with the board is too?
This one.
Okay,
It's,
let me open it up. There has to be another one that's not working.
there's only,
Did you notice another one?
Mom, was there another dead, outlet?
Just,
I gotta answer. Alright.
do you mind if I put you on hold 1 second, honey? Thank you so much. I'm talking to.
This is not a dedicated, I don't think it's a dedicated line. So it has-
Okay, yeah.
It has to like jump, so is there another one not working behind here?
This room is funny because the only other outlet is right here. I have a ridiculously long extension cord that I'm using for that computer.
That one?
Yeah, it works, but that one is not.
Something else, somewhere.
Sorry, I was hoping an old person on the phone. They're like slowly like, I'm trying to help them account, like send money between them. And they're like, what? You should pause it. I do it. There's no pause button. Let me end the phone call with her because she's probably okay. She was literally just, she wanted me to walk her through something on the thing. So, we'll be right back. Hi there, Patricia. The I believe it's just under $10,000 you're allowed to send back and forth.
It is possible.
So it is quite a lot. Do you know how much you were looking to transfer?
They put this box in, this was not in here. You know, this is added.
Okay, and it gave you trouble? Okay, what happened?
This wall is my kitchen. There's an outlet immediately outside. So my
Oh.
is my refrigerator. This one's right there. It's not technically.
I'm sorry that happened.
I know that maybe it's a little bit, but this is one.
I believe it's 10.
None of these old houses.
Mm-hmm. Right.
Is it back connected to the next one?
Next door?
Yeah, like that.
I understand. This was another, this was a loan perhaps you had another, with another bank or a credit card? Okay, I understand.
This, when I was here from the beginning, this place. is-
Oh, okay.
The stuff that's in the basement, I touched it and stuff.
Oh, wow, what bank was this?
Threw it away. It was literally melted. That's how they get fired, you know? The guy put it on the breaker.
Citibank?
So when you turn the light on, it was arcing.
Oh, okay,
It
okay.
burnt the wire.
How long ago?
I don't know. I just got it to the panel.
Just, as a
Mm.
side note, when we had the snow a couple of weeks ago, I lubricated the doorknobs because of the ice, so I just sprayed them with utility. You know, in the process, I took it upon myself, this is late at night, to spray the doorknob of the room that we just
Right.
And only because I was there,
Right.
only because I was in proximity to
Um,
the breaker, did I hear it.
I understand.
The silver
So,
pack-
I did, I just wanna correct what I said. Just under 10,000 was for check deposits. My apologies. My superior just informed me that
I didn't see it.
$2,000 is the daily limit for express. So in other words, it would be an instant transfer. If you did a standard payment, which would be about 1 to 2 business days, it's 5,000. So, it might be better to do 2 5,000s in this case, or two, like a 5,000 and 3,000 if you had about
We gotta check
8 in
this
total. Or
It's telling, it's giving you a sign, something is wrong.
Right.
it's 8,000 and
First one, right?
it's 8,000 in total, right?
The one that's empty.
I guess, yeah, probably
Okay.
just sort of driveway kind of on it, I suppose.
Okay.
You shouldn't be doing it, there's nobody there, there's no.
A wire might be better in this case. Like a wire is a little bit different than a bank to bank. So let me see what they say. Let me look up.
It comes from somewhere else. It has to be something that's not, something
That's something I could take care of. Do you mind if I call you back? I actually have the electrician at my house. I need to take care of something. Yes, Patricia. The phone number is, I have a 973 number and I have an 862. Which would be better? 862? Okay. As soon as everything's taken care of, I'll call you right back. Okay?
but directly
All
on
right. Thank you.
is the
Take care.
renovation.
Bye bye.
Yeah. It is directly beyond this wall.
The demolition guys, whoever did the demo, cut the wires and, removing.
I think they want to on sheet rock, so I figured they probably were digging up the wall.
Sorry, that was a quarantine.
No, I know.
This person is trying to pay off a loan, right? And their loan is over $8,000, so you could do a wire transfer for large transactions. Say you wanted to buy a house, alright, or some kind of property that's usually that's good for. We have a limit of how much you could send bank to bank. It's 5,000, so it's not enough. But she was having a hard time understanding.
What's directly, what's,
The neighbor's apartment downstairs.
Danielle and Shelton.
Probably the baby's room.
Downstairs, tenant, I think it is their baby.
Yeah.
It's the, where the porch is downstairs, that's the window that's on the porch is their wall.
I don't know if they're
I don't think they're home.
where's this
My extension cord is right here, so this, I'll show you. The outlet is there, and the extension cord is running along this wall to run this computer. I unplugged everything, like I turned the power switch off.
and you were getting power from this?
I was getting power from that particular outlet literally like a day ago. It just suddenly stopped. It was weird. I don't know. I was wondering if maybe the construction downstairs was affecting it, or I overwhelmed it because I have a lot of computer stuff in here. So that's why I turned everything off. I was worried.
It
about
didn't flip a
the
breaker though.
Yeah, but it didn't flip. So.
I wouldn't, have too many extension cords with a lot.
Downstairs. You have a GFI here?
What's that?
I'm just taking out, something is.
Oh, ground full circuit?
Yes.
Only around the bathroom. Like that outlet over there doesn't have one. We have one here and actually where the water is. when it's all, it's actually functional.
Yeah.
Yeah.
It's not,
It's a little worn, I guess, huh?
yeah, it should trip.
This is interestingly connected to this. I guess
Yeah, the other outlet.
if that trips, these lights go off.
It's-
That
it's
outlet is
dumb.
attached to it.
Crazy.
Yeah. This is my little teaching operation here.
Yeah,
Yeah, working at home is weird.
we gotta go downstairs.
Okay.
You mean in the apartment downstairs?
Yeah, I gotta know to the panel,
Oh,
that flashlight, where did they?
Oh, there. Mhm. Hey Google. Hey Google. Hey Siri.
could plug into that outlet?
Yeah, let me plug it.
Test it now.
Let's see again. It did?
Yeah, there's no smarts on it.
I have to find that remote. Ah,
There it is.
okay, great.
It's a different panel.
Are you kidding me?
No, no.
Where is it?
It's a panel that's adjacent, but it's not the ones. That one outlet.
Can we please label it?
He can't really because it would take forever, but maybe
Can we label it?
I'll
Like just a
remember.
green piece of tape or
I
something?
will certainly remember, but the truth of the matter is, it has to be replaced.
Really? It's old?
It's a little corroded.
No.
Check the bottom outlet.
Okay.
Right.
Yeah, it works.
Great. Okay.
The switch just went on.
All right. the main breaker.
Oh, he's replacing it.
He's replacing it now, and the one that is specifically that switch.
Should I unplug it?
I would, just to protect the television.
Okay.
But just be aware, we're not gonna have any power while he's
That's
working on
fine.
it.
I'm on break now. So it
Okay.
doesn't matter. I'm glad I went on break early.
Okay.
I was begging my superior. I was like, Chris, please. Because this woman was like, on the phone. I'm like, oh my god, shut up.
I'm gonna tell him now.
Okay.
panels are very screwed up.
What's wrong with them?
They're kind of like mixed a little bit, not drastically, but one of the all switches is in a different panel.
It's just mine, or is it?
That outlet is in
Yeah.
a different panel.
What about your room? Is your
My room seems to be okay. He tested it right at the source. So,
I'm sorry you're gonna.
if there is anything wimpy,
Mhm.
it's a very adorable kitten. Very.
Oh, I think it's Melvin.
Is this?
I'm pretty sure it's one of the.
Yeah.
I just found that picture randomly. I was like, oh.
I gotta tell him though.
Okay.
So all the lights are on. You know what? Let me just look.
Yeah, I'm almost certain that's Melvin.
See. Refrigerator still
There's a
functional.
picture of Duke on here too.
Alright, what'd you say?
There's a picture of Duke on here too.
Oh. Math people. Jeez, I gotta get back to work here. I am very sorry to leave you hanging for like an hour. Alright? You're a good sport to wait. Anyhow, just to explain, we had a serious electrical issue that is now resolved, thankfully. And the electrician can only come during the hours in which I work. So I didn't want to turn off my camera because then I would have to combine two videos, and that's just to make this even slower. So anyhow, if you're watching this when the time comes, right, just forward through it to the point where I'm talking now. Right?
You should put in a time.
I don't have time for that. I got too much to do. Anyhow, we are nearly finished.
There's no time for you guys.
My sister as a comedian, yeah. We ain't got time for you guys. Thanks, Mom.
I was messing with you.
Alright.
Just to check.
Your phone ringing or what?
It's telling it, yeah,
No.
it'll have.
Alright, here's a couple of fun facts. I'll just put this here, because this is where we left off. 1 kilogram is approximately 2.2 pounds. If you're ever wondering what LB stands for, it's from Latin again. This is way back from Roman times again. Libra Pondo. Is it spelled with an A? Yeah, Libra, like the astrological sign, Pondo. 1 pound weight, right? The scales. That's what LB is. Anyhow, man, my hands are dirty. 1 kilogram. Pardon me. I'm losing my mind here. There's something. 1,000 kilograms, right, is equal to what is referred to as 1 metric ton. And I'm going to spell it the correct way, T-O-N-N-E, right? And it is abbreviated by a lowercase t usually. At the same time, there's a ton in the Imperial System, right? 2,000 pounds is equal to 1, for lack of a better phrase, American ton, so T-O-N, right? And that is usually abbreviated by capital T. Alright, so anyhow, the good news is that because the definition of the volume of 1 liter is 1 kilogram of water at standard temperature and pressure you could actually interchange this allows us to interchange between basically unrelated units. So like we use liters for a volume, right? But we can actually translate that into a weight, mass I should say. The definition of the volume of 1 liter is that it is 1 kilogram of water at standard temperature and pressure. Now it depends on which standard you're following, all right? But 1 atmosphere pressure, which is normal, and maybe I don't know if it's freezing point or which would be 0 on Celsius scale. That would be more likely if it's from the scientific perspective, but some precise temperature and pressure. All right. This allows us to interchange, as I mentioned before. All right. 1 cubic centimeter is equal to, all right, 1 milliliter. All right. And that is equal to 1 gram. All right. which means that 1,000 cubic centimeters is the equivalent of 1,000 milliliters, right? Which is equal to 1,000 grams. It's 1 to 1, right? Now, these other two units, instead of saying milliliter, is just the same as 1 liter, right? Instead of saying 1,000 grams, all right, this is 1 kilogram. They're easy to convert from because of this definition. Right? 1 kilogram of water at a precise temperature and pressure is the volume of 1 liter. Now, why involve temperature and pressure? Because the temperature would cause it to, in theory, expand, you know? Depending upon what temperature it is, it would be slightly expanded or not. All right? The pressure as well. Okay, now. This is going to be a 4.5-hour video. Now that you have that, I'm going to not erase this because it's going to be potentially useful. Let me give you a volume problem. And I'll just draw it to get it quickly executed here. Alright. Alright. If you had a fish tank, which I'm going to draw in perspective here, with these dimensions, it's a rectangular solid, of course, right? This is a fish tank, which I will try to simulate water. A rather turbulent fish tank, all right? With these dimensions of it being 1 meter in this dimension, all right, 250 millimeters in this dimension, and 50 centimeters in this dimension, right? If we have this condition, all right, then how many liters of water would fit? Right, maximum. And what would be its mass? Right, in kilograms. Okay. Not the most eloquent explanation here, but this is a fish tank. I've stolen this from the textbook, this question, I'm pretty certain. Alright, with these dimensions, 50 centimeters, 1 meter, and 250 millimeters. There's an exercise naturally there in converting between those to one type. But then we're going to incorporate some kind of conversion factor to figure out two things simultaneously, one after the other. Right? How many liters, all right, of water would fit, and what would be the mass in kilograms? Right? We have to start with, if we're going to find the volume of this, right? Because that's liters is implying volume. And identify what shape this is. I mean, it's badly drawn, and I apologize, but this is what? This is a rectangular solid. So the formula we use would be length times width times height. All right? If I substitute, all right, the dimensions of, it doesn't matter what you call length or width or height, mind you, but if I substitute it in 50, say, well, to me it would be more intuitive to say it's 1 meter long and 250 millimeters wide and 50 centimeters tall, or height, right? It wouldn't be wrong if you identified these things, switch them, because we're just multiplying. But you'll notice that the units are not all the same. So we would ultimately have to convert them all to one unit. since we have conversion factors established here that we're involving cubic centimeters, it probably would be to our advantage to specifically make everything in centimeters, right? Which means what? It means that we'll leave 50 centimeters alone, because it already is centimeters, but then we will convert millimeters to centimeters, right? Remember the scale, right? If milli is on the very end and centimeters is next to it, and you're starting here and going there, it would be one space up, all right? One jump. So this would become 25 centimeters, right? If we're going from meters, and this would be decimeters in between, that is starting here and then converting to centimeters, that would be two jumps in this direction instead. So we would make two waves, right? You might just have it memorized naturally as well. What's the definition of a meter in terms of centimeters? It would be 100 centimeters, right? So you would have to multiply 100 times 25 and times 50, right? In doing so, let's see. I'm a little frazzled right now, so I'm gonna do this brute force stupid way. Times 25 times 50. All right, you would indeed get 125,000. All right, the volume is 125,000 cubic centimeters. All right. Now, if I'm going to answer this question of, well, what is that volume in liters? All right, I'm going to have to employ a conversion factor. The one that would be practical would be the conversion factor that relates these two, right? 1,000 cubic centimeters is equal to 1,000 milliliters, better known as 1 liter. So what I can do is multiply by this conversion factor, right? And arrange the unit cubic centimeter and liter in a way that would cause a cancellation effect. So if I want cubic centimeters basically to go away, I would have to put them down here. And if I want liters to be left over, liters would have to be here. All right? So that will then force you to put the numbers in the appropriate places. It will ultimately decide between whether you're multiplying really or whether you're dividing. All right? Well, 1 liter is 1,000 cubic centimeters. Now you could certainly use your calculator, but you could also employ tricks. Remember, if you have 3 zeros here, you can knock off 3 zeros here. That's dividing without really thinking about it, all right? And that leaves you with just 1 times 1 as a denominator, which is superfluous, you don't need it. And then just 125 times 1, which means what? It means that this is 125 liters. Right, to answer the question of how many liters of water would fit in there. All right, then there's this next conversion. All right, they're asking how much would it weigh. All right, well, what it would be its mass to be more precise. Well, we know this relationship. All right, that 1 liter is 1 kilogram really, because 1,000 milliliters is equal to 1 liter, and 1,000 grams is equal to 1 kilogram. So it's a 1-to-1 relationship. So without really going into it, you could also, you could write a conversion factor as you see I have done here, all right? But it would be like this, all right? It would be maybe a little unnecessary. 125 liters times the appropriate conversion factor that eliminates liters, because it will be down here, and gives you kilograms. And the relationship would be 1-to-1, so it really isn't going to change anything. What would the mass be? 125 kilograms. All right. All right. When you get comfortable with it, you will call it a godsend. Right? I'm telling you, if you haven't taken chemistry yet, right? This is the kind of thing that you'll see them do a lot, right? And God bless the chemists that they teach it this way, because it's an intuitive system. If you could decide that, well, I want to get rid of this and I want to keep this. Right? You could be strategic in how you arrange the parts, and you don't have to worry about the legal reason as to why. Right? That's okay. It's a conversion factor. It's a tool. All right? All right? So anyhow, we are going to revisit this in the subsequent class when the time comes. All right. Now the next thing is this. I'm going to draw a diagram and I'm going to do 2 problems for temperature and then we're finished. All right. I'm very sorry for the hiccup in between. Let's see. We have temperature scales that we need to consider. So there's, familiar to a person from the United States, there's Fahrenheit scale, Fahrenheit. That's how I remember how to spell it. That is a German sounding name if I've ever heard one. Kind of like Ziegler. Fahrenheit. Alright. And then there's the system that is akin to and used and incorporated in the metric system, right, which is the Celsius scale. Celsius. These aren't too far apart in time if you want to associate. The Fahrenheit scale, I believe, is from 1724. All right, that's when it originated. And the Celsius scale is a little bit after it, 1742. Coincidentally, the same digits in a different arrangement. All right, this is named after Daniel Gabriel Fahrenheit. Right, who was a German living in Poland, basically, at the time. Germany is a country, I believe, unfortunately, stretched into Poland at this point. Another famous person from that time frame would have been, Kant, Immanuel Kant, all right, who was both German, but he was in Poland, technically, by today's standard of a border. Anyhow, this is a person, Anders, who I think is the coolest name, all right? I have a kid, named him Anders. Anders Celsius, all right? He was a Swede, all right? Anyhow, the Fahrenheit temperature scale is based, they're actually based upon the same ideas, but using different increments, if you will, all right? This is based upon the freezing point of water or, I mean, initially it might have been brine, like a pickle solution, you know, but nowadays we consider freezing point of water and the boiling point of water. Water, right? This is also based upon that. Boiling point, freezing point. But you'll see a distinction here. On the Fahrenheit scale, basically the difference from here to here, if you think of this as a point and this is a point, all right, is 180. Now, why do you suppose that number? Does that seem familiar? I can't help but sense that that is some kind of a weird superstition, right? The number 180 has been with us as a number, a quantity of significance since at least the Babylonians, right? Right? So, if you study trigonometry, you know that half of a circle is 180 degrees, right? A full circle is 360. It's not a coincidence that 360 is the number of degrees on a, in a circle, and very remarkably close to the number of days in a year, right? Anyhow, these numbers linger, all right? And in this case, Fahrenheit must have decided that the difference between the freezing point and the boiling point would be this magic number, for lack of a better phrase, all right? Anyhow,
into Celsius, took the same idea, all right? This is a point on a scale, all right? But instead of it being 180, it's 100, all right? That's the magic number. And arguably, that's the better of the two choices, because 100 is a power of 10, and 10 is very intuitive to us. Right? 180 actually is based upon 60, and 60 comes from our hands as well, as you know. Right? The little notches on your hand, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 5, all right, is 60. Anyhow, there's two formulas, all right? And they're here on this sheet, all right? 9/5 it comes from the conversion factor of 9 over 5, which is 180 over 100 simplified, all right? Essentially, all right? I put this in there too so that you see that, you know, we have this idea that, you know, 0 degrees is cold, right? On the Celsius scale, it would be -18, you know, all right? And so forth, all right? All right, let me do these two problems, all right, and that will be it for today. If you want to convert, if you want to continue with this diagram, right, what would be appropriate to put on the Fahrenheit side would be the Fahrenheit formula. This converts to F, right? So Fahrenheit is 9/5, which is basically a conversion factor, the ratio of 180 degrees to 100 degrees, right, times Celsius plus 32, whatever your degrees are in Celsius. If you want to convert to Celsius, degree mark, we use the same naught symbol in the superscript. It would be C is equal to 5 over 9 times the quantity F minus 32. Right? It's the ratio of 180 over 100 flipped, right, and simplified. So, again, you have this information. I'm going to do these two word problems here, right? This is essentially asking you, in the case of, it's labeled example 4 on the sheet, convert 55 degrees Fahrenheit, right? I'll put it here just to not take up too much space. If you're essentially going to have to convert 55 degrees Fahrenheit to Celsius. All right, which of these formulae would be more appropriate to use? All right, you're given Fahrenheit, but Celsius is what you want, so this would be the appropriate of the two. All right, which means you're going to stick 55 in here. You do have to be mindful of the order of operations, which means that although there's multiplication involved here somehow, there's a parentheses here intentionally. You are obligated to do the subtraction first. All right. So what's 55 minus 32? All right. This should be 23. All right. If you treat it as though it were a fraction, since this is being multiplied anyway, it's the equivalent of 5 over 9 essentially times 23 over 1. If you could simplify, I would. In this case, you kind of stuck with crummy numbers, so you got to use what you got. All right. End up with what? 15.
Yes, they are.
You end up with 115 divided by 9, which means that in terms of, once you've divided this, all right, you're going to get a decimal. You should get something like, what is it, 12.8 degrees Celsius. Okay? 9 goes into 11 once with 2 left over. 9 goes into 25 roughly twice, which is 18. The difference of 18 and 25 is 7. Alright, so it'd be 7 and a 0. And 9 goes into 70 roughly 8 times. No, it would be 7 actually, because it would be 63. And I'm running out of board space here. Alright, you're going to get a decimal of 12.7 something, that's rounded. Alright, so let's see, 115 divided by 9, 12.7 repeating. Okay, yeah, so about 12.8. Okay, this is approximately. Alright, now if you're doing the other one, alright, and you're essentially asked to convert, let's see, 60 degrees Celsius into so many degrees Fahrenheit, right? You're given this, and this is what you want, it would be more appropriate to use this formula, all right? In that event, you would put 60 here, all right, and then straighten it out. In this case, there's no parentheses, but there is multiplication, which would take precedent over regular adding, all right? The way the math would work out, you have essentially 9 over 5 times 60 over 1, and you would simplify to spare yourself some trouble. This would be 1, and this would end up being 12, and this would be 108 plus 32, right? All right, what's 108 plus 32? 140, right? You should end up with 140 on the nose. Okay, so 12.8 and 140 degrees Fahrenheit here. Okay, thank you guys for sticking with me all this while. Again, if you find these handouts useful, please do print them. I'm going to have them available in Canvas, right? Logically, what you would have for homework, just to remind you, I updated this, so you'll see that you have another slew of my lab homework that's due at the beginning of April, right? So for right now, immediately do, or at least try to, do my lab sections 7.1, 7.2, 7.3, and there would also be a prerequisite naturally, prerequisite to measurement. Okay? Sorry how long this is, just skip through the middle, alright? Maybe if I have time I will annotate. Alright, anyhow, see you next Monday. Okay, be careful.